Welcome to the next lecture on root finding techniques. Today we're going to be doing the second one that we're going to look at in this section, and it is a method called the method of false position. It's one that's been used for a long time. It provides us with another approach, and I think it's kind of interesting. You might look at the board and wonder what that's all about, but essentially this method has a second name, and we're gonna I'll give you the answer to the question of how that way is pronounced in a slide or so. But yeah, it's really interesting because bisection method is a method that always works. If you have a function, you know that a root is bracketed on some interval between a and b. There has to be a root in that interval because one side's negative and the other side's positive. We know that bisection method is going to work to find that root. It's just that sometimes it's a bit slow. And the other techniques that we talk about in the next couple of lectures will present us with some better methods under certain circumstances that will really speed things up and get faster convergence. So let's talk about that. So yeah, I don't think it's going to be the longest lecture, but it's a really interesting one in terms of how this thing works, and we're going to see it in practice. So as I said, there are other more sophisticated methods that have been developed that tend to work more quickly than the bisection method. And the first one we're going to talk about is this method of false position that I mentioned. And it's also called, it's this word, and to be totally honest with you, I had never been sure how to pronounce that until I started teaching the course. And after doing some considerable research and so on, I can confirm that I think most people pronounce it falsi and not falsi. Although I'm sure that people would know what you were talking about one way or the other. If you're not sure, just call it the method of false position. You can't go wrong that way. In any case, what is this thing? Basically, it's the next step forward. It's like a smart version. A smart version of the bisection method. And it's actually been used for literally hundreds of years, not thousands, okay? If not thousands. It's been used to find roots of a function f. And like bisection method, it relies on the intermediate value theorem. Okay, it still involves the evaluation of the endpoints a and b of an interval that is known to contain a root. So there's nothing different so far in the setup between this and bisection method. But what it does is it chooses a different point in the interior of that interval to subdivide the interval at each step. And it does this in a way that typically causes the estimate to converge to a result faster. What estimates you choose might depend on what your results are. There are different choices you could make, and we're going to see in an example that it might be good to choose our estimates as actually one endpoint of the interval rather than the midpoint. But that could depend on the function as well. So here's how it works. What is that different point that we choose in the middle? Well, okay, we're going to start with a function f that we're interested in, a starting interval, a0, b0, and we know that that interval contains a root. Same sort of setup as bisection method. But here's what we're going to do. We're going to consider the line segment connecting a0, f of a0, and b0, f of b0. So I wonder, do I have a graph down here? I don't think so. Okay. Maybe I'll draw something afterward to kind of show you how this works. So we've got a line segment connecting a0, f of a0, and b0, f of b0. And rather than just dividing that interval in two, we're going to find the x-intercept of that line segment we draw between the two. And because of the fact that one of a0, f of a0, and b0, f of b0 is going to be below the x-axis, and one will be above, then by intermediate value theorem, that line segment has to pierce the x-axis. That x-intercept has to exist. It must exist due to intermediate value theorem. Okay, we're going to call that point x equals c, and we're going to evaluate that f of c. We'll use that c value at which the function will be either positive or negative, and use that and the one endpoint which f is at the opposite sign to get a new smaller interval that brackets the root. This should be a b with this of brackets, like this. Okay, so this is essentially the same thing. We're just using a different c value in the midst rather than just kind of blindly dividing it at the interval in half and then continuing that process forward. So you can see that kind of in terms of flow, it's going to be really, really similar to how bisection method works. The only sticky step is therefore figuring out what the heck that line segment should be. Because if we want to figure out what the root of that is, we're going to need what that line segment is, and that's going to involve a little bit more calculation than simply dividing an interval in half and taking the midpoint, you know. But we can use some simple functions to do this. Let's remember the equation of a line that connects 2 points, because that's what we need here. The general formula, of course, is y minus a y point, y1, equals m times x minus x1. And I'm going to apply this situation to this formula with f of a and f of b and a and b. So essentially, the a and f of a, think of like an x1, y1, and the b, f of b being x2, y2. And this is the formula that we're going to use and apply it to. And so this is what we get when we sub in. You can see f of b is y1, x1 is the f of a, and so on. And if I want to find the x-intercept of this thing, which is what the process is here, that's given when y is equal to 0. And so this is just going to be 0 minus f of b equals f of b minus f of a over b minus a times x minus b. Our goal is to solve for x if I want to find the x-intercept for this. So let's isolate for this. That shouldn't be that hard. I need to multiply up by the b minus a. I need to divide down by the f of b minus f of a, and then I need to add the b. So it looks like we're going to get the following. Minus f of b times b minus a. I'm going to do this in 2 steps so I don't screw this up. We have f of b minus f of a times x minus b. And our last step, I'm going to divide down that f of b minus f of a now. So I'm going to get f minus f of b, and then b minus a over f of b minus f of a. And then we have to add b plus b equals x. So this is what it looks like. Okay. We have to do that repeatedly. So this is going to give us our x, that x-intercept, and this is going to be defined as our c value. And so this is going to be done repeatedly. We're going to evaluate that c value. We're going to see if that's positive or negative, find a new interval that brackets the root, and then repeat the process. So this is the scheme that's going to be what we use repeatedly. So I've tried to kind of show you this in this formula down here, which is our general scheme at step k of the process. These are a sequence of a and b values that we get, and the c at each step, the c that we use to redefine the interval, is given by this setup, which is justified by the line above. So it's a little bit more involved, for sure, to find what that c is. But it's still not hard, and it's certainly something that, especially given a computer, can be something that is pretty effective here. So, yeah, I guess I want to kind of just graphically show what's going on here. Which I wasn't sure if I had any graphics to show off here. But let's suppose we have a function, and we know that it has a root somewhere. So let's draw this thing like this. Who knows? Maybe that's my function f. And suppose we have an interval, and it's here to there, we say. Let's let this be a, and let's let this be b. What's literally happening here is there's my f of a. Here's my f of b right here. So f of b is up here. And if I go to find the line segment connecting the two, actually, let's make that green as well. There it is, right there. I want to make this a dotted line too, just, there we go. Okay, whoops. We can see the C value that we would get on the next step here would be right here. Our C value would be here. And then you could see that the root, if I were to evaluate f of c, it would be negative. So I'd then take that and our b as the new interval that would then bracket the root, and we could repeat the process again. And by doing this, we're going to get a series of intervals that's going to converge in on the result. Again, choosing our actual estimates to be somewhere in those intervals. So this is kind of a graphical depiction of what's going on at every step and how this is going to kind of whittle down that interval. Okay, let's apply it to an example. And we're going to use the exact same function that we did for bisection method, but this time we'll see how this works. And again, the flow is so much like bisection method. We have f of x equals e to the minus x, and we're using a starting interval of 0 to 1, and we're going to find an estimate for a root to f after iterating the process 3 times. So let's do that. So let's see, we have a couple of things that we know. We could evaluate f of 0 to start, that's 1. We could evaluate f of 1 to start. And if you throw 1 into this, and I'm using 0 and 1 because that's my initial interval, I get negative 0.6321, which I think we saw before. Our current interval is the interval 0 to 1. And what we're going to do is try to find our c. It's not a matter that c is going to be 0.5. C is going to be determined by using that calculation, that scheme from before. So that goes like this. C is equal to, it's minus f at 1, and then we take 1 minus 0 over f of 1 minus f of 0. Okay, we're going to take that, and we're going to add 1 to it. So let's make sure, let's verify that this all lines up okay. We have that c is equal to minus f of the b, and then b minus a over f of b minus f of a, and then we add b. So you can see that this follows the same structure right there. So then it just comes down to, can you evaluate this darn thing? And if you do, it works out to this. It works out to 0.6127. Okay. With that 0.6127, that's going to be the thing that we use instead of the midpoint, the 0.5 that we would have used for bisection method. But we still need to evaluate the function at this to see whether it's positive or negative. So then, f of that 0.6127, if you throw this into your calculator, just put that into your original function, and that should give you negative 0.0708. All right, so this here is going to be one of the endpoints of the new interval. And I want to choose the endpoints of the new interval so that they still enclose the root. And I see that the answer here is negative. So I want to choose the one out of the original two where it's positive, the plus one that appears here. So my new interval I get to is going to be 0 to 0.6127. So that's one iteration. One iteration is complete, and we're going to move on to the second one. And I'm just going to redraw what we've got here. We know that f of 0 is 1. We know that f of 0.6127 is negative 0.0708. And our current interval is 0 to 0.6127. And our job is to find a new interval. So we're going to do the exact same thing that we did before. This time, our c is going to be given by minus f of 0.6127, and then 0.6127. It gets kind of repetitive, which is why it's nice to program a computer to do this for you. F of 0.6127 minus f of 0, and then plus that 0.6127. Okay, if you work this out, it's nice that you have, right, you see why it's useful to have f of 0 and f of 0.6127 at the ready there. So you can just refer to them and put them in here and go forward. This works out to 0.5722 according to my calculations. Hopefully I didn't make any mistakes there. Okay, and we don't want that. We want f of that to check. F of 0.5722 works out to negative 0.0079. Okay, at this point there are a couple of things I want to note. First of all, this and that are going to bracket the root. But it looks like for this example, that right endpoint, x equals 0.5722, is itself getting very, very close to the root. Why is that? Well, look at it. If you evaluate the function at that value, you can see that the value that's given is something very close to 0 already, less than 1/100th on the negative side. And so while we have this big interval, it might not be the best idea to choose the midpoint for this interval as our estimate. You can actually look at this, see that, well, one of the endpoints is getting very close to that root, and use that as your estimate instead, being a little bit pragmatic about things, okay? So it's a little bit interesting. That'll depend a lot on the function, on what the outputs are, and so on, but it is really nice to see us converging toward values somewhere in that interval. And we could be smart about what we choose as our final estimates. So we're going to do one more, so that's 2 iterations down. And the third iteration is going to use f of 0 equals 1 and f of 0.5722, which is minus 0.0079. And I'll let you do these calculations, but this will produce c equals 0.5677, which then gives an f of c of negative 0.000896. And you can see quite clearly, I'm going to box this one up instead. You can see that this estimate is getting even closer to the true root. So very close to 0. And it's really just through a sequential version of what I drew in that one example up there. We're drawing lines, finding x-intercepts, and coming up with new intervals. And it just so happens that our x-intercepts are themselves getting very, very close to the root. We're actually going to see this on the next technique that we deal with. It's going to deal a lot with secant lines. It's called the secant method. And this method that we're talking about here is really good practice to talk about that other method. So there's one thing that I want to mention, and I didn't mention it before, but it's an important sort of thing here, is that, yeah, oh, I guess I talk about it later, but there's one interesting aspect about this, this method. You notice that in every single step when you go to calculate c, you have this denominator that appears. That's the subtraction of 2 items, an f of b minus an f of a. And in theory, you could have a function that wiggles about and gives you a 0 on the bottom there. In that case, obviously the method's going to fail. So we have found a first condition where we have a technique that could fail under a particular circumstance. So we're going to want to make sure that if we do choose a starting interval, that the denominator doesn't get too small, and certainly that it's defined in order to make sure that this works out. And if we get to a spot where we get a 0 on the bottom or something close to 0 on the bottom, that could throw off our results. And we would need to make sure that we start with a different opening interval or something like that to ensure that we don't get a 0 on the bottom. Okay, so a little bit on coding here. I'm not going to go into a huge process because this is so darn similar to bisection method, right? The flow is exactly the same. You start with a beginning interval, an a to b. You start with an initial function, the f. The only difference that occurs is how you define c, because c is going to be given by that calculation of the ratio of items and the addition of that extra b and so on. You have a more detailed, more complicated line where you're figuring out what the c is, the test point. That's literally the only difference. And so I want you to think about doing that, but I'll give you a couple of tips before you try. So when it comes to MATLAB and that symbolic package, sometimes what happens is that if you feed MATLAB a particular set of calculations to apply to a number, and you have a symbolic variable, it won't evaluate it exactly. It will apply the operations to it to give something super, super exact. For example, rather than see an answer of like 1.41 at some iteration, you might actually see square root of 2. And rather than see a decimal expansion of whatever a complicated set of commands is, you'll see literally that complicated set of commands applying to your number. And that would just grow and become very hard to process for human eyes after many steps, because it's just going to grow and have more and more commands applied to it to give an exact answer. So this is because it's treating numbers as exact symbols rather than outputting a decimal approximation. Okay, so the one thing I want to introduce at this point is the double command, okay? It's going to give you a floating point approximation to quite a bit of precision of whatever is inside the brackets. So if you write, here's this exact answer, the example that I was giving before. If you write f of 3 after defining f of x equals square root of x, you get 3 caret symbol 1 over 2, just to be absolutely precise. Whereas if you write double f of 3, the MATLAB output will be 1.7321. Basically, it takes that, gives you the best approximation possible, and you can use that in the next iteration to continue to get decimal approximations that are helpful for us to understand and process. So the point is that when you replace that C, instead of doing the midpoint like you would for bisection method, you're going to be doing a more complicated sort of set of calculations and so on that involve B, A, and F. So instead of using this code, which is simply going to apply all those different calculations and not reduce anything down, imagine doing that 10 times. It's going to like take that result, put it in to the next, and it's going to grow in size and possibly clog up your program. You should probably instead use code that looks like this. Simply take the very same thing and throw it inside a double command. C equals double of that. Keep that in mind as you go forward. That's going to be really, really helpful to make sure that you continue to have an efficient program that doesn't come to a slow or a stop because it's trying to keep all of this detail in mind as it processes. Okay, so I want you to use your new powers here. For you to try, I want you to go back to bisection method, which hopefully you were able to code after the last video, and adapt your code in order to do false position. All right. Once you do that, we can talk a little bit about convergence here at the end of this lecture. It turns out that you might get to a result a little bit more faster. It's a bit of a more intensive method. There are some more calculations involved, but convergence typically happens faster. The thing is that it's not that much faster. In fact, it has been proven that despite the fact that on average it does a little bit better, the convergence for false position is still only linear. just like bisection method. But perhaps, if you remember back to our definitions of order of convergence, perhaps it has a smaller asymptotic error constant, the lambda in that definition. So minor improvements of speed, but it is about as it has the same order of convergence, the same like overarching governance of how fast the algorithm works. There's a good reason that we covered this though. There's a good reason because I think it gives us a really good start for our next point of conversation. And our next point of conversation is on a very powerful method that does increase the order of convergence. And it's called the secant method. And it's going to use secant slopes and a lot of the same sorts of tools, but it's going to throw out some aspects that we talked about here with false position. So I hope you'll join me for that. There's lots to practice with and for you to try on both bisection method and now this second method. And there will be more to come with our next couple of lectures on secant method and Newton's method. So join me then. Until then, take care of yourselves, take care of each other, and have a good day.